So, students, today we are going to discuss some important topics in electricity. First is resistance. Now, according to Ohm law, we all know that potential difference across a conductor. We always say potential difference across a conductor, right, is proportional to the current flowing through it, that is the flow of discharge per unit time. Now from this we got V by I ratio is always constant. Voltage divided by current, well, this is constant, and this constant is basically R, which is resistance. The unit of resistance is ohms. All right, guys. Now, resistance can be varied also by using rheostat. Now, the interesting thing is, you see the mathematics going in this. Let's say you have a rheostat and you decrease the resistance and I. As you can see from this equation, they are inversely proportional. I can say resistance is inversely proportional to current, making two things constant, temperature as well as a voltage. Maybe you see that, battery attached to this conductor. So when the resistance somehow, with the help of rheostat, if we increase the resistance, the current would decrease, and if you decrease the resistance, current would increase. In which fashion? In the fashion that V is equal to, from this equation, IR. That means the product of I and V is equal to the potential difference. V is equal to IR. Well, this is one concept we have discussed. Based upon this, you can do some formulae. Then the second thing is factors on which resistance depends. Even resistance, it depends upon some factors. Now, we do a small experiment. Let's take, we take a conductor AB. We in series have ammeter which can measure current, and then we, from the ends A and let's B, it is connected to a battery, right? Let's say this is a 2-cell battery. Now, what we do, let's say the original length of the conductor was L. Original length was L. Now, if you double the length, what do you do? You double the length in first case, and then you see the ammeter reading when you double the length. Interestingly, the ammeter reading is halved. That means whatever was the value of the current, when the length was L, the value got decreased by I by 2. In case I was the initial value of the current is halved when the length is doubled. Now we know from this that R and I are inversely proportional. The current would decrease only when resistance is increased. So we could make a judgment from this experiment that when we double the length, the resistance must also have been doubled. The resistance is also double because, in this experiment, we're making temperature and voltage constant. In the second judgment, what we did, well, this is area of cross section, maybe a small, let's say this is a rod, kind of rod, or kind of the copper rod. And I've just shown it as a straight line. Let's say it has this area of cross section, which I'm showing it on a magnification scale. So now, initially, let's say the area of cross section was small, area of cross section was A, and now I have increased the area of cross section, making the length constant. In the first case, I had double the length, making the area of cross section constant. And what I got was current was halved. From this, I made a judgment that resistance must have been doubled. So resistance changes. When resistance changes, when we change the length. Now we change the cross section. Now we change the cross section area. And again we saw making the length constant when we increase the cross sectional area, what we observed, the current increased. When you increase the cross section area, the current increased. So from this, what we infer, the resistance must have got decreased. So from this small experiment, we came to know that resistance is increasing, length is increasing, means resistance is directly proportional to length. And from the second one, when the cross sectional area is increasing, we have seen the current is also increasing. Current must have increased when the resistance is down. So that means when the cross sectional area is increasing, resistance is decreasing. In other way, you can say when resistance is increasing, when the cross sectional area is decreasing, the resistance would have increased. That means resistance and cross sectional area, they are inversely proportional. Resistance is inversely proportional to cross sectional area, which I represent by A. From these two judgments, I could combine these two parameters, which are length of the conductor and area of cross section, because it is possible that simultaneously I increase the length or decrease the length, and I replace this conductor with more length or less length, with more cross sectional area or less cross sectional area. In that case, what would be the change in resistance? The resistance from the first case is directly proportional to length of the conductor. And second is resistance is inversely proportional to area. So I write it combinedly in the form of resistance is proportional to L by A. In this indirectly, it means resistance is proportional to length. Resistance is proportional to area, cross-sectional area. More the length, more the resistance, more the area of cross-section, less the resistance. Now students, again, when we want to remove the constant of proportionality, we have to introduce a, yes students, we have to introduce a, tell me students, when you want to remove the constant of proportionality, you have to introduce a constant here. Always remember. So we say R is equal to L by A will remain same. Here I will get a constant that is represented by Greek letter rho. Guys, R is equal to rho L by A. This rho, students, is known as resistivity of a material. Resistivity of a material. Now, students, to tell you frankly that this resistivity is kind of more basic, more fundamental property of a material as compared to its resistance. So, when we talk about, the blockage for the flow of current, it is the resistivity, which is the considered, which is a property of the material. Now, what is the unit of resistivity, students? Let's see. The unit of resistivity, from this we came to know R is equal to rho L by A. Now, let's write, whenever you want to find the units of something, very simple, write down units of everything except this one. R is ohm is equal to rho into length is meter, area of cross section is meter square. Meter cancels with square. Now rho is equal to meter into ohm. So this is ohm meter. The unit of resistivity, unit of resistivity of a material is ohm meter. Always remember that. All right. So this is another thing we have studied. And now I also want to tell you that the metals and alloys have very low resistivity. Metals and alloys, they are good conductors of electricity, and their resistivity is in the range of 10 raised to power minus 8. This is not watt, this is ohm meter, to 10 raised to power minus 6 ohm meter. They are good conductors of electricity. Insulators like rubber and glass, or maybe cork, they have resistivity of the order of, their resistivity is very, very high. This is not 10, 12, this is 10 raised to power 12 to 10 raised to power 17, not watt, ohm meter. So this is the reason insulators, they completely block the passage of current. So almost you can say completely, because this value is very, very high. Okay. Now resistance and resistivity of a material, they vary with temperature, and that's the reason we assumed that we will make temperature constant while doing the previous experiment. All right. Now this is a table which shows the electrical resistivity of some substances at 20 degrees centigrade. We're making temperature constant. So this is ohm meter, unit of resistivity. Silver is having a resistivity of 1.6 into 10 raised to power minus 8. So what does that mean? Very low resistivity. Very low resistivity means a very good conductors of electricity. So then comes copper, aluminum, tungsten. You know, you know that you use it for, they once used it for, converting the electrical energy into optical energy, right? Done by Joseph Swan, and then later by Edison, right? Well, we normally give credit of electric bulb invention to Edison, but then you don't forget Joseph Swan, all right? Chromium, mercury, manganese, and then when we talk about alloys, constantan is this, it's alloy of copper and nickel, and then nichrome. This is the resistivity. If you talk about insulators, obviously they'll have, you see, these conductors and alloys, they have resistivity in like 10 raised to power minus something, very low resistivity. But if you talk about insulators, the resistivity is very high. This is 10 raised to power 10 to 10 raised to power 14. If we talk about diamond, resistivity is 10 raised to power 12 to 10 raised to power 13 watt ohm meter. Uh, the resistivity is given. Fine. You got a rough idea about resistivity. Now, students, let's do small numerical. What is this numerical? How much current will an electric bulb draw from 220 volt source? So this basically battery is 220 voltage, right? And there is a bulb basically. We have a bulb here. I'm not able to draw properly. I'm sorry. So you can also say this is a load. You know. Now we want to find out the current, how much current the bulb will draw from 220 volt source if the resistance of the bulb filament is 1200 watt. The resistance is given, bulb filament is basically 1200. I'm sorry, this is not watt. Resistance is given in ohms. This is also ohms. So in first case, we talk about a bulb and we make some good judgment. In other case, we talk about electric heater, which we normally use in our house in winters. Now, when the R is 1200, ohm, and voltage potential difference is 220 volt. According to Ohm's law, potential difference is directly proportional to current, or V by I ratio is constant equal to R. So obviously from this we could get I is equal to V by R cross multiplication. So V is 220 volt. Always write unit, students. It will give you a good habit. And R is 1200 ohm. Right, so this is equal to whatever it is, you just divide it. This is like 11 and this is like 60, so it's very less, 11 by 60 for ampere, very less than 1 ampere current, less than 1 ampere current, maybe 0.6 or something ampere. Now if you talk about a heater, so this bulb is drawing very less amount of current from the battery. Its resistance is very high. Its resistance is 1200 ohm. You see, when resistance is very high, the current is very small. It's less than 1 ampere. Doesn't it satisfy Ohm's law? That resistance is directly inversely proportional to current? It does. When resistance is high, current is less. Now, students, another thing I would tell you, in case you replace this bulb by something which will have less resistance, it will draw more current from this. Interesting. Still, if something has less resistance, it will draw again more current from this battery. So if we have different loads here, it doesn't mean they will all draw same amount of current. They will draw different amount of current depending upon their resistance. That's the beauty of Ohm's law. It will give you the value of current by dividing the voltage or potential difference by the resistance of that. As we do in the second case, and now the voltage is again 220, resistance is this, so the current would be 220 volt by its 100 ohm. So very simple, this is equal to 2.2 ampere. So it is lot more times more than the current which electric bulb was drawing from the battery. So we come to know a new thing, good judgment, that as the resistance of different things are changing, the current drawn from this will also change, such that I into R is equal to 220 volt. All right, students, hope you learned something. Wait for more videos to come on electricity. Thank you.